right, so let's do another example of estimating beta hat here. So here's my design matrix. I have a vector of 1s here as my first column, and then I have two predictors, x1 and x2. Now, do you think that x transpose x is going to be invertible? So the first check is, what is n and what is p? So we've got 4 rows and 3 columns, and so 4 is greater than 3, so we're good there. Should be invertible, at least by that standard. And the next is whether these are linear. This is a linear combination. So it's close, but it's not quite a linear combination, so I think this is going to check out. Let's see. All right, so when I take the determinant of this, it is close to 0, but not quite 0. I end up with 0.0056. And when I take the correlation between the second and third column here, I end up with 0.9999993. So very close to 1. They're highly correlated, but technically not perfectly correlated. And so yes, I can take a transpose of this, or I can take an inverse of this matrix. And in fact, I can calculate beta coefficients. I end up with 1.28, negative 114, and 57. So that's my beta hat 0, beta hat 1, and beta hat 2. Now, what is the equation for the variance of beta hat? This might be a bit of a refresher from before, or maybe, well, we did talk about this when we talked about linear regression. So this is going to be from just about 2 weeks ago, but it's going to be that sigma hat squared times x transpose x inverse. And so it is multiplied by that, the inverse of this matrix. And so again, in order to get this variance, we have to be able to take that inverse, which in this case, we can. Technically, we can get that inverse. And that sigma hat squared is going to be the residual sum of squares divided by n minus p plus 1. This is going to be maybe a little bit of a refresher from your stat 2 days. But this is basically the estimated error for your model. Okay. So if we multiply that estimate times x transpose x inverse, this is what we end up getting for our variance of beta hat. And so here, our variance for beta 0, this is a variance covariance matrix. And the way that we interpret this is along the columns are the values for beta 0, beta hat 1, and beta hat 2. And along the rows are beta 0, beta hat 1, and beta hat 2. And so what that means is this value here is equal to the covariance between beta hat 0 and beta hat 0, which is equal to the variance of beta hat 0. So the variance of beta hat 0 is this 9.918. This here is the covariance between beta hat 1 and beta hat 0, negative 24, which is the same as the covariance between beta hat 0 and beta hat 1, negative 24. This value here, this 12, that's the covariance between beta hat 2 and beta hat 0, which is the same as the covariance between beta hat 0 and beta hat 2, 12. Okay, so the variance of beta hat 1 is 0.91. There we have it. What about the variance for beta hat 1? What do you think that is? That's going to be this value here, and oh my goodness, it's huge, 4,081. That is a very large variance. Why is it so big? It's so big because we're multiplying by our x transpose x inverse here. And this, even though it's possible to take this inverse, it ends up really being large because these are highly, highly correlated. So this is important that sometimes even when we can take that inverse, it's going to give us some answers that are going to be kind of wonky, especially if our predictors are highly, highly correlated. Okay, so sometimes we cannot solve for beta hat, and that is because x transpose x is not invertible. It's not invertible. This happens when we have more variables than observations, or when the variables are linear combinations of one another. Even when we can invert x transpose x, things can go kind of wrong, like we just saw on the previous slide. Like the variance can blow up, like we just saw. So when you have highly correlated variables, even if they're not perfect linear combinations of each other, even if you technically can take an inverse of that x transpose x, you can end up with these really large variances when you deal with these highly correlated variables. So what can we do about this? Well, this is all building up to the method that we're going to be talking about today, ridge regression. So what if we add a penalty that will keep those beta hat coefficients small? And this is going to keep the variance from blowing up. This is kind of a brilliant idea. Instead of minimizing the residual sum of squares like we do with linear regression, we can minimize the residual sum of squares plus some penalty function. So we're going to be minimizing the residual sum of squares plus this shrinkage penalty. And so this shrinkage penalty is going to be some value lambda times the sum of the beta coefficients squared. And so what happens when lambda equals 0? So let's look at this equation. When lambda equals 0, this is going to get negated. So this is going to drop out. And we're just going to be minimizing the residual sum of squares. And as lambda gets bigger and bigger and bigger, then this quantity here is going to get larger and larger as well. So let's solve for those beta hat coefficients using ridge regression. What are we minimizing? So now we're going to be minimizing this y minus x beta transpose times y minus x beta, so that's our residual sum of squares, plus lambda times beta transpose beta. And so I can rewrite that sum of the beta squares as just beta transpose beta when I'm writing it in kind of matrix or vector form. Okay, so what I want you to do is in your RMD file that you've been working on, I want you to find the beta hat that minimizes this. And so if you need to, pull up your notes on how we did this first part, because that's going to be exactly the same. So you're still going to FOIL this, and you're going to take the derivative with respect to beta, but now you have one extra piece that you need to make sure you take the derivative in terms of. And then, of course, set that derivative equal to 0 and solve for your beta coefficient or beta hat.